Welcome everyone to today's Autonomy Talks. It's a pleasure to have Robin Brown with us today. A few words on Robin. Robin is currently a PhD candidate in the Institute for Computational Mathematical Engineering at Stanford. Before that, she has received her Bachelor in Mathematics, Business, Economics, and Management with a minor in Control and Dynamic Systems from Caltech in 2018. And her work focuses on the design of hybrid quantum classical algorithms for optimization, with a specific focus on optimization problems that arise in robotics and control. And we're very happy to hear from Robin more on this today. The stage is yours, Robin. Thank you.
Awesome. Thank you. Thank you so much, Mark, for that kind introduction. And I guess thank you to Duality for inviting me here today. Hopefully you'll see this later. But I'm very excited to be presenting my work in this seminar, especially since this isn't my typical audience for this talk. However, as Mark mentioned in the introduction, my own background's more on this optimization and control side of things. So I think that this community has a lot of insight that could really be impactful in the realm of quantum computing and quantum optimization. So hopefully by the end of this talk, I want quantum computing to be a little bit more approachable, and I want to try to convince you that it's both a tool that is worth looking into and that you have the expertise to work with as well, if not now, sometime in the future. And for the most part, I will be presenting this talk in the language of more classical optimization. So hopefully that should be more familiar with you for all of you. But if you have any questions, since it seems like a pretty small group, I would encourage you to just interrupt me and ask them throughout, and we can kind of play around with that. Cool. Okay. So in the past few years, we've seen a lot of pretty flashy headlines about quantum computing, and particularly some of these devices that these companies are building. And they're usually accompanied with a very flashy, very cool image like the ones that I have on the slide here. So we have these giant cooled computers, or we have these teeny tiny little chips that people are working with, and they seem very interesting. But also with a healthy dose of skepticism, it might seem very futuristic, and it's kind of difficult from these headlines to distill what the near-term impact of these technologies will be. And I'm sure that when you saw the title of my talk, the initial reaction was probably something along the lines of, okay, that might be interesting, but realistically, when will we be able to solve problems that we actually care about on quantum computers? And to what extent will they change the landscape of problems that we work on in our lifetime? So if I'm working on difficult optimization problems now, is this going to change the course of what I do? Is it going to make some of the work that I do obsolete at some point in the future? And if you have started looking into quantum computing, or if you kind of have a base level understanding of it, you might have come across some of the more foundational algorithms in this space. One of the more famous ones is Shor's factoring algorithm, which everyone is convinced is going to break encryption, right? But you might have encountered some of these algorithms that are kind of very highly tailored to the specific problems at hand. And then once you try to understand them, partially due to the different language barrier across fields, these results can be very difficult to have an intuition for, especially since they use different notation for matrices and vectors than we typically do in optimization and control. So if you were to look at quantum computing as a tool, just as a tool to use for your problems, the barrier to entry might seem very high. But in the same way that I'm not an expert in, say, the way that my Python code is turned into machine executable code, that doesn't stop me from coding in Python. So I think that there's certain high-level abstractions that you can work with instead of getting too in the weeds of quantum computing. So one particular abstraction that we see a lot is the abstraction called an Icing problem. And that's basically a discrete quadratic minimization problem over the positive and negative one variables, like I have written on the slide here. From a very quick change of variables, this can be reformulated as a minimization over binary variables instead. So you'll often see the term quadratic unconstrained binary optimization, or QUBO for short, in the literature. And that's basically exactly what it sounds like. So there's nothing more to it. And there's actually a number of different devices that implement the Ising problem directly. So the probably one of the more famous being the D-wave quantum annealer. You might have seen that. You might have seen that in popular, I guess, news, or the coherent Ising machine, which is a network of degenerate optical parametric oscillators. But you don't have to worry too much about like what those devices implement exactly. There's also algorithms that are designed to solve or approximately solve Ising problems on gate-based quantum computers, such as the quantum approximate optimization algorithm, or sometimes that's abbreviated as QAOA. And actually, all of these methods and devices can be run right now, like on a device right now. However, the caveat is that there's still a lot that we still don't understand about their behavior. So for example, we might not get the global minimum of this optimization problem, but we get a good quality approximation instead. But then again, we don't understand, like, we don't have guarantees on what the gap is to optimality, which is something that we typically have to work with from a classical optimization point of view. And also, one of the open questions in this field, and like when it comes to these devices, is actually like benchmarking the speed up over classical optimization. So they want to do that both empirically, but also analytically. And that's still an open question. And there's debates about the right way to do that. So even with those caveats in mind, even though the Ising problem formulation might seem super restrictive at first, there's actually this paper in 2014 from Andrew Lucas that showed that all of CARP's 21 NP complete problems can be reformulated as Eisen problems. So this gave people a lot of hope that their practical problems might have a way to translate into Eisen problems directly. And I think the analogy that you should think of here is that after you learn about linear programming or any of the other standard convex optimization formulations, so like quadratic programming, SDP, semi-definite programming, and so forth, you probably looked at like the problems that you cared about and tried to see if there's a way to fit them into these existing templates, like problem templates, right? And if there's a way that they fit, then you're in luck because you just kind of reformulate them and then toss them to an off-the-shelf solver, and then you get your solution back, right? So in the same process, many people try to take their problems and then fit them directly into this Ising form. And actually, when we started out this project, we were looking at a very specific problem. So we weren't looking at copositive optimization generally, but we were looking at neural network verification very specifically. And that's basically the approach that we tried to do with this. We tried to take it and really force it into this Ising form and see what would come out. But there's a number of things that really didn't work for us, so that we weren't able to make this approach work for us, partially due to some of the limitations of the Eising solvers itself. And that's actually the motivation for the work that I'm going to present here today. So in the verification problem, basically we have a trained neural network. So the weights and biases are fixed. And you want to check that for all inputs that belong to a particular input set, whether the corresponding outputs, so after you feed it all the way through your network, whether the corresponding outputs belong to some other output set, right? So you can see how this might be important for representing certain safety objectives before you go and deploy a network in the wild. So for example, if you have a network that classifies stop signs, you might want to make sure that all minor perturbations of stop signs are still classified as stop signs. So like in this image on the slide here, you probably want to make sure that the stop sign on the right is not a speed limit sign or a go or a green light, right? Or if you have a network that condenses a lookup table of aircraft advisories, you'll still want to make sure that this new condensed network is still effective in preventing collisions, like this ACAS-X example that I have on this slide here. So it's a pretty foundational problem in terms of being able to deploy networks in the wild. And it turns out to be NP complete. So this problem is actually pretty well studied in the literature. So if you go and look up neural network verification, you will find a lot of papers on this topic. And there's one approach, there's one standard reformulation as a mixed integer linear program, whose global optimum indicates whether you satisfy or violate your safety rule. And the way that you basically do this is by introducing variables that represent the values at each of the hidden neurons. And you'll use constraints to ensure that variables in corresponding layers, in adjacent layers, basically correspond to the relationship from the weights and biases, right? And then you'll also use constraints to enforce your activation functions as well. But the key thing here is that the global optimum of this mixed inertial linear program corresponds to safety or violation. So unless you have a global optimum, so unless you have guarantees of optimality, a heuristic solution doesn't mean much in this case. So when it comes to forcing problems into this Ising form, there's kind of a standard workflow that's emerged. So if you look up problems that use like quantum annealers or Ising problems, then you'll typically see this approach no matter what the problem is. So the first thing is that the Ising problem can only deal with quadratic problems. So you'll take any polynomial terms in your problem and kind of expand them out by introducing auxiliary variables that represent higher order terms. So then it kind of reduces your problem order to quadratic. Then if you have any constraints in your problem, since the Ising problem is unconstrained, you'll take your constraints and you'll move them into your objective using a penalty function. Then finally, if you have continuous variables, you'll discretize those so that you can represent them using binary variables. And then finally, you're going to take this and then pass it off to your Ising solver and then read off the solution, often with little or no post-processing afterwards. There's a couple of key challenges when it comes to this approach. So the first being that when you put constraints into your objective using a penalty function, you have to keep in mind that these are couplings that need to be implemented in hardware. So when you might think of dragging your penalty constraint up to infinity on a classical computer, that's something that you can't really do in hardware, because in hardware, when you drive your penalty constraint up, it's going to start to wash out the effects of your objective, right? So then you can think, if you're trying to enforce constraints using a penalty function, you end up with these very sharp peaks and valleys that make that optimization landscape pretty hard to deal with from a practical standpoint. But then if you don't enforce your constraints enough, then you're not enforcing your constraints and your solution can violate those. So then you have to very delicately tune what your penalty parameter is to kind of hit that sweet spot in the middle of enforcing your constraints and trying to optimize your objective. The next thing is that when you discretize any continuous variables, there's an automatic discretization error that comes with that. So you might be motivated to use a superfine discretization to try to capture those continuous variables faithfully. The issue with that is, number one, it's very costly in terms of the number of spins that takes. And these are all physical qubits. So if you look at the headlines, there's a very limited number of physical qubits on these devices. So you want to be very cognizant of how many additional variables you need to add into your problem. The other issue is that since the binary coefficients kind of get folded into your objective, this now introduces a high skew in the couplings. And like the issue I mentioned in the first point, you have to implement these in hardware. So you can't really have as many bits of precision that you might be used to on a normal computer. So you have to be careful with those. And finally, if you make it through these two steps and still manage to keep track of your approximation errors at this point, you pass it off to your Eising solver, and you still get no guarantee on optimality. Because like I mentioned when discussing these Eising solvers, at this point, they're all kind of heuristics and we're still trying to characterize their behavior. So even if you were to manage to keep track of everything until this point, you kind of lose those guarantees once you pass it to your Eising solver. So like I mentioned, when it came to the verification problem, we really needed guarantees of global optimality. So this just could not work for us. There is no way for us to make this work for us. And when we were looking at this workflow as a whole, so looking at this entire stacked workflow, it became pretty clear to us that unless your problem already very naturally fits the Eising form, forcing it into that can produce some very undesirable ill conditioning in terms of the number of variables, the coupling strengths, and the optimization landscapes. So it also seemed like many of the limitations of quantum computers are actually strengths of classical computers, right? We don't think about the precision to which we can represent numbers on a classical computer. We don't think about whether it can reliably carry out the commands that we program to it, right? So instead of throwing this all away, it seems very natural that classical computers should be working in the loop with quantum computers to try to help mitigate some of their shortcomings. And ideally, we would come up with a division of labor where each type of computer is only used for what it's good at. But at this point, it's kind of unclear of, okay, like what is good for a quantum computer, what is good for a classical computer. So what is this perfect division of labor? And that's actually something we'll get to throughout this talk today. So for the rest of this talk, we're going to kind of go through a journey of like some existing quantum computing methods, so existing hybrid quantum computing methods. I'm going to give a brief introduction to copositive optimization because it ends up being a very useful tool for understanding hybrid algorithms. And then finally, I'll end with discussion of our hybrid copositive cutting plane algorithm. So let's get started on that. And hopefully, like along the way, these should be pretty good breakpoints to kind of like ask questions or regroup if like we lost you along the way, because there's a lot that's going on here. So the first thing that we're going to discuss is kind of the analysis of hybrid algorithms, because when we were looking at the literature, this was something that hadn't been really formalized before. And thinking about what we want from a hybrid algorithm, so what's desirable in that case, was a key stepping stone for even being able to articulate what the right objectives are for designing hybrid algorithms. So I'm going to kind of go over a few of those objectives that you might think about, and then piece together some of the strengths and weaknesses of some methods that exist in the literature. And that will help us put together a full picture of what we actually want in this space. So our ultimate design goals for a hybrid algorithm. So when I first started working on this project, I expected to be able to abstract the quantum computer as a standard component in a randomized algorithm. So you might have some failure probability, you might have some optimality gap, and those are known a priori. And if you've worked with randomized algorithms before or read anything about randomized algorithms, knowing these failure probabilities and optimality gaps beforehand is actually very critical to the algorithm design. So I think that the crux of many of these algorithms is that you design the algorithm by finding the perfect balance between like failure of the randomized components versus its efficiency. However, as I mentioned in the introduction, even getting provable guarantees on these performance metrics are open questions and ongoing research at this point. So we have to design algorithms. So unlike standard randomized algorithms, we have to design these algorithms without knowing these values and being able to count on certain performance metrics of these components. So everything in this quantum side is, you might think it's good, but not really, you might not know how good it's going to be, right? And we can't count on those for designing our algorithm. The next thing that you might care about is when you look at the algorithm as a whole, whether it converges to anything at all and what it converges to. So kind of looking at the neural network verification problem, we wanted guarantees that our algorithm was converging to something, and that something had to be close to our global optimum. So we'll want to ensure that our algorithm is getting a meaningful answer at the end, which turns out may not be true of many hybrid algorithms that exist. And finally, you'll probably want to consider the complexity of the classical portion of your algorithm. So when your classical computer is working in the loop with your quantum computer, you'll want to make sure that the operations that it's carrying out at each iteration are somewhat efficient. So you'll want a characterization of that. You'll also probably want a consideration of the number of total iterations that your algorithm needs to run. And then you kind of piece this all together and derive some value on the total classical complexity of your algorithm. And you probably want that to be at least efficient compared to the difficulty of the problem that you're solving, right? And I think that this aspect is a little bit overlooked when it comes to quantum or hybrid quantum classical algorithms, which is basically whether the quantum computer is actually addressing the bottleneck in your problem. So I think that people try to say, like, okay, where is the Eising part of this problem, or what parts of the problem can I make this Eising? But there's no guarantee that that Eising part is the bottleneck of the problem. And that's kind of one thing we saw with one of the approaches for verification as well. And that's an important consideration to ensure that you're actually getting a benefit or speed up from using the quantum computer. Because just because there's a quantum computer in the loop somewhere doesn't necessarily mean that you're getting a benefit from it. So you kind of want to, and because we can't reason about the quantum part itself, we kind of have to use deductive reasoning about the classical part and say, like, okay, at least the bulk of the complexity is not on the classical part, so it must be on the quantum part. Okay? So that's one of the key differences when it comes to designing these hybrid algorithms. So I went over the direct transcription approach, where we kind of put Eising problems directly into this, where we took our problems and moved them directly into Eising problems. So now there's kind of this rich literature on hybrid algorithms that exists out there. And the nice thing about them is that they're basically all rooted in existing algorithms, either for convex optimization, non-convex, or discrete optimization. So that means that we can repurpose the analysis of the classical versions of these algorithms to try to derive derive an intuition for what the hybrid version can get us, right? Or how the hybrid version behaves. And this kind of gives us hope that if we just pick the right classical algorithm as a starting point, we can derive the analysis and methodology from there, and we don't have to completely design a new algorithm from scratch. So I'll go over some of these branches of these trees and discuss some of the considerations that I came up with. And that will be helpful for understanding what the limitations of these algorithms are and what our goals were at the end. So on this branch of the tree, I have everything that I label under exhaustive search. So this includes both Bender's decomposition and taboo search type approaches. So in Bender's decomposition, it was designed for algorithms that are characterized by a set of complicating variables. And once you freeze those complicating variables, the rest of the problem becomes easy in some sense. So you should think of mixed integer programming, where once you fix, or mixed integer linear programming, where once you fix your integer variables, the rest becomes a linear program and thus easy, right? And the way that Bender's decomposition typically works is that you have a master problem that's handling these complicating variables, and then subproblems that deal with the easy part of the problem, right? But the issue with Bender's decomposition is that when you look at their convergence guarantees, they typically depend on exhaustive search through your complicating variables. So your guarantees are not based on efficiency, but basically because you can't revisit solutions. So that means in the worst case, you're searching through all of your complicating variables, even if there is a quantum computer in the loop. And there's some variants on this Bender's decomposition approach, where people use the quantum computer to generate cuts, or to select cuts, basically. And in that case, they still have their classical computer solving a mixed integer program. So there's no guarantee that the complexity of the problem isn't going to show up in that mixed integer programming step. And the taboo search basically uses a large neighborhood local search using your Eising solver, and then use local improvements on the classical computer. But there's no guarantees of convergence of the taboo search in this case. There are some guarantees in some classical versions, but they depend on now including a recency or frequency memory. That basically means you're not going to cycle through your solutions. So when the proof of convergence is based on going through all of your solutions, there's almost no hope of getting efficiency in the worst case. So it might be it might have practical advantage, but you can't prove anything about where the complexity is going to show up. So another approach that's been explored is based on the alternating direction method of multipliers, or ADMM for short. And basically this was a classical convex optimization algorithm to decompose large-scale optimization problems into smaller subproblems. So while it was designed for convex optimization, it's worked pretty well as a heuristic for non-convex problems as well. So people have started to study its convergence in non-convex cases. But its convergence guarantees tend to be pretty strict in non-convex cases, relying on what are called the Kurdeko-Lojasiewicz conditions. So it's not necessary that that always holds in non-convex problems. And often the convergence is to a stationary point and not to a global optimum either. So we don't necessarily have guarantees on where those stationary points lie in relation to our global optimum. And some people have looked at the proof of ADMM with hybrid algorithms, or looked at the proofs of convergence of ADMM with hybrid algorithms. And their proofs hold in the case where they're only dealing with binary variables, but once you look at the continuous variables, their assumptions break, basically. So there's no guarantees of how this is going to converge and how well. And finally, there's a pretty interesting approach based on Graver bases. So this is designed for purely integer programming. And the idea is to compute a Graver basis of the null space of your constraints. And they formulate that as an Eising problem. The issue, though, is that when it comes to non-convex problems, the size of your Graver bases might grow exponentially. So then they've had some workarounds, some multi-start methods to kind of work around this exponential complexity. But then once you go to this multi-start methodology, that now becomes a heuristic. So there's no guarantees of convergence in this case either. So I think that this is a very interesting approach, and it's very closely related to the copositive work that I'll talk about here, but it's not quite everything that we need. So basically, we're going to put all of this together, and it motivated us to ask the question of whether it was possible to design a hybrid algorithm that can convert the black box and heuristic solutions from our Ising solver to ones with rigorous optimality guarantees. And then we want to do so without introducing an exponential overhead on top. So if you look at the considerations I've laid out previously, this addresses, one, our lack of knowledge of the Ising solver guarantees, two, the convergence of the overall algorithm, and three, the efficiency of the classical portion of the algorithm. So these are our design considerations moving forward. So when it comes to analysis of optimization algorithms, you might have noticed that the analysis comes a little bit easier in convex settings. And this is primarily because in convex settings, local information can be used to derive global optimality guarantees. And when it comes to looking at non-convex problems, the analysis tends to be more specialized depending on the problem itself. So of course, when it comes to solving problems with a quantum computer, we want to be able to address the really hard problems and move beyond standard or efficient convex programming. And one paradigm that we found that's able to kind of bridge this gap between the non-convex and convex worlds is copositive optimization. And it gives us a very interesting convex perspective of traditionally non-convex problems. So in this portion of the talk, I'll give an introduction to copositive optimization and try to give a little insight for how these formulations are derived and what they buy us in terms of analysis. So at this point, we're going to kind of narrow down our focus and look at a very specific problem class, which is those of mixed binary quadratic programming problems. So these are characterized by a potentially non-convex objective, linear equality constraints, non-negativity constraints, and some of our variables may be binary. So I looked at neural network verification to start with, and this is representative of neural network verification. This can also be representative of model predictive control and many NP-hard problems, such as maximum clique and scheduling and routing. I haven't included it on this slide, but this can be for notational simplicity, but you can expand this to include complementarity constraints as well, which we're looking at in terms of ways to represent hybrid dynamics. So for the rest of this talk, if you're familiar with semi-definite programming or SDPs, this will all be pretty familiar. And I think when it comes to understanding copositive optimization, it's pretty instructive to look at SDPs and look at the intuition that you have for SDPs and try to just go one step further to copositive optimization. Okay, so the way that we're going to start to work with copositive optimization is kind of the standard trick when it comes to SDPs of introducing a new matrix variable that represents the product of two other matrix variables. So while we started out this section working with just these little x vectors as our variables, we're now going to introduce big X as a matrix that represents degree 2 monomials of little x. So really, at a high level, you should think of the ijth entry of big X is equal to the product of little x and xi and little xj, right? So I think that the easiest way is to think about this visually. And the thing that this buys us is that it allows us to linearize quadratic expressions by using the matrix inner product. So I really like to write this out using the standard inner product notation. So with these two angular brackets to emphasize that it's a linear operation. So it's the same. You should think of it as the same as like any inner product when it comes to vectors. So this is often defined, or this is defined as the trace of the transpose of your first matrix times your second matrix. But the way that you should really think of this is that if you have these matrices, you're unfolding them into vectors and taking your ordinary inner product. Or another way that you can think of it is that you're taking these matrices, stacking them together, multiplying them entry-wise, and then summing that all up. So you should think of this really as just like an ordinary inner product. And the nice thing about this is that our quadratic expressions that we started with are now linear in this space. So then that allows us to transform basically all of our constraints in a similar fashion. So now if we look, we can now include two constraints that represent our original linear equality. So if we look at the first one, that basically just says ax equals to b, which was the exact constraint that we started out with. The second constraint that's introduced for the linear equality constraints basically says ax, the whole thing squared, is equal to b squared, because obviously if your constraint holds, then its square also holds, right? And the second and the constraint that represents the binary variables, it can be a little inscrutable when it's written out like this, but it basically just says x squared is equal to x. So the only values of x that satisfy this are x being equal to 0 or 1, so binary variables. So if we look at this, this means that the objective and the constraints that we're dealing with now that we've lifted to this matrix space, are all linear in our optimization variables. So then what's the catch? The catch is that we have this non-convex rank 1 constraint that basically destroys convexity of this problem. And now we can't really work with that or get easy optimality guarantees given this rank 1 constraint. The standard approach for dealing with this, and if you've worked with SDP relaxations, you'll have gotten to this point, right, is to relax this rank 1 constraint and then replace it with a PSD constraint instead. And the reason that this is only a relaxation and not exact is that when you work with this PSD matrix and you get your solution out, you'll typically try to factor it to recover the variables from your original problem. And what happens when you try to factor that is that you might find that each of the factors do not correspond to feasible solutions for your original mixed binary QP, right? But instead, so none of them satisfy all of the constraints, but when you kind of mash them together, they combine together and mask each other in a way that seems like they satisfy the constraints as a whole. So that's where relaxation gaps come into play when it comes to SCP relaxations. So this should all be pretty familiar. So we're going to take this one step further, and there's actually some pretty minor changes to SDPs called copositivity and complete positivity that actually buy you exactness in those cases. So the definition of a copositive matrix is basically that if you take the quadratic form of that matrix with any vector in the non-negative ortho, that needs to be greater than or equal to 0. So if you're familiar with the definition of if you're familiar with the quadratic form definition of semi-definiteness, your test vectors will typically come from the entire real number space instead of just this non-negative ortho. And then when you look at complete positivity, the definition of that is that I want to be able to factor this into sets of vector products and vectors and their outer products. And each of these vectors needs to be entry-wise non-negative. So again, if you're familiar with an alternative definition of SDPs, you'll typically want to be able to factor it in this outer product form, but there's no requirement on the non-negativity of each of these vector factors. So basically, there's these teeny tiny restrictions or widening of these sets that are the difference between copositivity and complete positivity in positive semi-definiteness. So if you think of it, copositivity is a weaker condition than semi-definiteness because your test vectors now come from a smaller set than SDP matrices. But when it comes to complete positivity, this is a smaller set than SDPs because there's a restriction on what factors are valid for factorizing a completely positive matrix. And actually, even though these conditions or even though these modifications seem to be pretty innocuous, this makes the complexity of detecting whether or not a matrix is copositive or completely positive quite difficult. And if you look up, for example, non-negative matrix factorization, like there's a lot of very recent work on ways to do that because this problem hasn't been solved, right? But in a very celebrated work from 2009, Samuel Beer basically showed that pretty much all mixed binary QPs can be posed as completely positive programs. So the only thing that's changed from our SCP relaxation slide is that we now have a restriction on what are valid matrix variables to work with in this case. And this restriction, in fact, is enough to buy us exactness in this case, because it ensures that anything that's valid for this set of matrix constraints belongs to the convex hull of valid solutions in our original problem. So then, since we have that exact convex hull characterization, that means our final objective is also going to be exact. So this work was celebrated in 2009, but as I mentioned, dealing with complete positivity is actually quite difficult. So it doesn't really buy you that many computational advantages at this point. So I guess that's a brief overview of co-positive and completely positive optimization. And now we're gonna regroup and get into the algorithms. So hopefully this is the fun part of this. Right. So as a reminder, what we're working with in this section are these Eising solvers that I introduced earlier in this talk. So these discrete quadratic minimization problems. And what we were able to show is to take Samuel Beer's result and take it one step further and show that if our original mixed binary QP, it has a bounded feasible region, then this dual copositive program exhibits strong duality with the completely positive program on the right. So actually, this was a pretty technical result because if you examine the way that these constraints are constructed very specifically, there's no interior to these constraints. So your standard Slater's condition doesn't hold here. So proving strong duality between these two programs was actually an open question for, I guess, the past 12 years or so. So it was pretty nice to finally be able to close that door and prove strong duality between these two programs. And I think that parsing all of the matrix variables that are on the slide here aren't all that important. So I've kind of highlighted in different colors where each of these matrices come from, because they're all very formulaic from your original problem. So you don't have to worry too much about what these say. And of course, this kind of raises the question. I think that when I present this slide, I typically get the question of, okay, but if it's exact and it's convex, does that mean the problem is easy? And no, it doesn't. There's no free lunch here. But what this copositive representation buys us is that it takes the complexity of the problem and packages it entirely in the copositivity constraint. So the rest of this problem has a structure that we can very easily work with and very easily reason about. So if we look at this problem structure a little bit further, so we're going to maximize over the mu, lambda, and gamma variables. And if we look at this, we have a linear objective of our optimization variables. And we have a linear combination of these constraint matrices that we have a constraint on. And we want that entire thing to belong to the cone of copositive matrices. So that in itself, despite being hard to work with, is a convex cone. So at face value, this structure is one that should be very familiar when it comes to convex optimization. The difficulty, though, is that checking membership in the copositive cone is co-NP complete, but it's most naturally posed as a non-convex quadratic minimization problem, like I have on this slide here. So that should start to sound familiar because the Ising problems are discrete but non-convex quadratic minimizations, and what we need to solve here, or the hard part of this problem, is a non-convex minimization. So there's a very natural fit between Ising problems and checking copositivity. And the tool that we're going to use at this point is that if there's a negative solution to this quadratic minimization, that can be very directly used to construct a feasibility cut. So you can take any point, check if it's copositive. If it's not, you can use that solution to generate a cut that separates that point from the rest of the feasible region. And this is very reminiscent of cutting plane algorithms. So the way that cutting plane algorithms work at a high level is that you maintain some sort of outer approximation of your feasible region or your optimal set. Your classical computer or your computer picks a test point, you test feasibility of that point, and then you add a cut that cuts it off. And if you're very careful about the way that you choose these test points, so if they're in some sort of center of your outer approximation, you can make sure that you're making consistent progress in terms of reducing the size of your search space. So if you're familiar with binary search, you should basically think of this as high-dimensional binary search. So just in binary search, you choose the center of your interval each time, and that means that you can cut off half of your search space each time. So this is just a high-dimensional analog. And the way that we're going to divide labor between our classical computer and our Eising or quantum computer is that we're going to have the Eising solver check copositivity, and that's all it's going to do because of this natural fit between checking copositivity and Eising problems. We're going to have the classical computer carry out everything else. And as I hinted at earlier, there's a number of different cutting plane algorithms that exist out there, but we can start to repurpose the analysis that was developed for these algorithms and use those to analyze our hybrid algorithm. So all of these listed cutting plane algorithms vary in terms of kind of the resolution you use when it comes to representing your search space. So like how detailed that's going to look. So for example, if you have an ellipsoid that's not very detailed, you're representing your feasible region within the ellipsoid each time. Whereas like with center of gravity, you might keep all of the cuts that represent your feasible region. So they vary in terms of the resolution it takes to represent your outer approximation and the amount of effort it takes to compute the center. Because if you think about it, computing the center of an ellipsoid is quite easy, but when you have a complex polyhedral region, that might be quite difficult. Right. So then looking at the list of these complexity results, they're typically divided into the number of oracle queries, which in this case are actually the number of calls to our Eising solver, which end up being the number of outer iterations in our algorithm. And you can see in this space, these are all very efficient in terms of the size of our problem, which is denoted by dimension n in this case, right? So you can see that none of these are exponential in the size of our problem. And the total complexity, which basically includes the number of outer iterations multiplied by the complexity at each iteration, is also quite efficient, and they all tend to be polynomial time in the size of our problem as well. And these are pretty much optimal when it comes to convex optimization. So this kind of allows us, when I started this talk and I wanted to say we wanted to deduce the complexity of the classical portion, actually these numbers all represent the complexity of the classical portion of our algorithm. And all of these are just repurposed from the literature, so I didn't have to derive any of this myself. So then the other thing that's nice is that I motivated this talk, or I started out by saying that these Eising solvers may not be reliable in terms of getting global optimality guarantees. However, even though I've written these copositivity checks as a minimization problem, I don't actually care about getting the global minimum to it. So for me, any negative solution is useful and doesn't change the convergence guarantees of the total algorithm. So any negative solution can be used as a feasibility cut, and I don't really care if it's the most negative solution. Of course, the most negative solution corresponds to the deepest cut in this case, but which might have a practical convergence. It might have a practical convergence implication, but it's not necessary. And in fact, none of the analysis depends on that. So we're now tolerant or resistant to the fact that we don't have optimality guarantees of our Eising solver. And then, as I mentioned previously, all of these various trade-offs when it came to cutting plane algorithms just trade off the complexity of computing the center and the number of outer iterations. And pretty much all of them, except for the center of gravity method, ended up being polynomial time, the number of decision variables. So then if we kind of do this back of the envelope calculation, this suggests that all of the complexity of the problem is shifted onto the Eising solver. And this gives us hope that even if we don't have provable guarantees of what the speedup of the Eising solver is, we can still take advantage of it if it's there, right? So if there's any hope that it's there, we don't have to know exactly what it is, but we're going to put all the work on the Eising solver instead. So we kind of made these arguments analytically, but we also showed this practically speaking or empirically as well. So we tested out our copositive cutting plane algorithm on a maximum clique problem. So on the copositive formulation of that problem, and we benchmarked the rest of the algorithm and the copositivity checks separately, where the copositivity checks were solved using one of the mixed integer linear programming representations of copositivity. And what we were able to see is that this red part, which represents the copositivity checks, tends to be the bulk of the algorithm, right? And there's hope that if we take this and we're able to squish this red part down using a state-of-the-art Eising solver, so a quantum Eising solver, then we can really reduce the total complexity of this algorithm. And of course, this green part will remain regardless of what Eising solver you use here. So this is what we're stuck with. But I think that being stuck with the green part in this case is actually quite good. So this kind of confirms our claims that this shifts complexity onto the copositivity checks or the Eising solver. And we actually took this one step further and solved our copositive cutting plane algorithms with D-wave simulated annealing in the loop. We also solved the maximum clique problem heuristically with just D-wave simulated annealing, like working with the Eisen problem directly. So using that direct transcription approach. So in that case, we actually went through the effort of very delicately tuning that penalty parameter, and the D-wave plots correspond to that tuned penalty parameter here. And what we see is that our copositive cutting plane algorithm is just a little bit slower than the D-wave version of the maximum clique problem directly, which of course makes sense because you're solving a single problem in that case, and you're not trying to derive optimality guarantees. Whereas for this small price, we get optimality guarantees of our total algorithm. And what we see is that when we benchmark this against Gurobi, which also is getting optimality guarantees, Gurobi is faster on much smaller problems, but our scaling performs a lot better than Gurobi. So we're scaling closer to these state-of-the-art Ising solver. And when it comes to larger problems, we start to surpass Gurobi. And this gives us hope that since we're only using simulated annealing at this point, if we can bring this even further down using a quantum annealer, we can start to show real speedups over the state-of-the-art classical solvers. Right. So that basically concludes like the technical portion of this talk. And I think that the takeaway messages that I want to leave you with here is that these hybrid quantum classical algorithms are a new computing paradigm. And we really have to develop and think about new analysis frameworks. And from those analysis frameworks, write down what are desirable for hybrid algorithms. And that really hasn't been formalized before, just because it's a very new field. So I think that we have to be very careful about the way that we talk about these algorithms and talk about their guarantees. And none of the copositive optimization that I've presented in this talk is new. It's existed for decades, but it hasn't offered a significant computational advantage over dealing with more direct forms or more direct non-convex forms of problems yet. But I think that quantum computers and Ising solvers are an enabling technology for copositive optimization. And I think the analogy that I want to draw here is that, if you look at the history of machine learning, that really goes back to the 1950s. And it really couldn't take off until GPUs started to mature and could be adapted to make deep learning frameworks. And in the same way, I think that copositive optimization has existed, but Ising solvers and quantum computers are going to be the technology that really enable us to work with these copositive optimization frameworks moving forward and to derive efficient or optimal algorithms for non-convex problems. So the archive link for this paper is up on the slide if you're interested in this in any more detail. I wanted to thank the many wonderful people that, or I want to acknowledge the many wonderful people that have made this happen. And I would be happy to take questions if there are any.
Thank you for the great talk. And congratulations on the strong duality proof. I hear, it may not have been that easy. So congrats. And yeah, if there is anyone out there with questions, please feel free to unmute yourself or write down a question in the chat so that I could read it. Let's see if there is anyone. Otherwise, I'd just be curious. This is indeed the field that I think, at least from our side, we don't cross every day, especially the quantum computing seems very far out to us, I believe, on the robotics world at least. But I'm curious whether you have access to a quantum computer so that you can test the algorithms, this framework.
Yeah, so I think that, I don't get special access to a quantum computer, but I think that if you look at D-Wave and some of their open source software, actually you have access to a quantum computer if you wanted to, right? If you just kind of looked up what they have through cloud computing services. What I will say is that some of this work came from a grant that works specifically on the coherent Ising machine. So my goal by the end of my PhD is to run all of these algorithms on that machine.
Okay, that would be really cool. Yeah, looking forward to see, those results then. And,
Yeah.
that leads actually to the next question. Now, as you started out, you were also talking about the neural network verification,
Yes.
like on your path to solve that problem, if it still is on the horizon, where do you see yourself now after all the progress that you have made?
Yeah, so I think in terms of the neural network verification problem, I think that, so there's a couple of things that I kind of left out of this talk, and in particular, moving from the continuous copositivity checks to a discrete approximation. And I think that being able to implement those copositive or those continuous variables natively is going to be the key to actually being able to use verification. Just because kind of the discretization errors that I've discussed previously are still a consideration here. So actually, that's kind of our ongoing work is ways to implement these copositivity checks natively. I think that along the way, though, we kind of discovered that. So in the realm of neural network verification, there is a whole literature on designing SDP-based relaxations of that problem. And due to the similarities between copositivity and SDPs, we were looking at these relaxations and saying like, hey, like the copositive representation of this problem gives us a lot of insight in the ways that we want to design SDP relaxations. So even if you don't go all the way to exactness, there's a lot of insight to be gained from this. And we actually had a paper, I think in 2021 on this. So I'd be happy to link that as well.
Mm-hmm. Yeah, that would be great. I think in the meantime, there was a question in the chat. So Harsh is asking whether there are any information-related limits to this copositive approach to quantum control.
That's actually a topic that we haven't looked into of like information, I guess,
limits, yeah.
Information complexity-based limits. But I'd be happy to discuss discuss further offline.
Okay, yeah, I think you have your email is linked to the talk later on. So, if people would like to reach out, are they free to send you an email? Yeah,
definitely. I'd be happy to take any emails and to chat basically anytime. So
great. I think if there is no other question, I have last. Okay. So Guanchun is asking whether quantum mechanism essential to Ising solvers, since there seems to be some Ising machine with only classical dynamics?
Yeah, nope. You can actually look at all of these results from the lens of purely classical Ising solvers. So our results, or our empirical results, were based on D-Wave simulated annealing, which is just a classical simulated annealing algorithm. So all of the results, I think that I underemphasize this part, but all of our results apply to heuristic Ising solvers and even heuristic classical optimization solvers as well. I think that like the way that we look at maybe like learning-based heuristics should also apply in this case.
Okay, thank you. One question that I had that I think ties in with this is, when you showed the charts, the box plots, the red and the green ones, where the red was, I think, the quantum solution, and red the classical part, or sorry, the other way around, red the quantum, green the classical part. Once you're able to push down everything below the green part so that there is only the classical part, say, expected to be the limiting factor, would this allow you to tackle the problems at the scales that you would want to use this for? Or would you foresee that there still needs to be some development on the classical parts of this interface so that overall you could scale it to the scale that you would want to?
Yeah, so I think that it depends on how far you go along your, I guess, axis of size of problems. So I think that in terms of tackling problems that are larger than we've tackled before, this will certainly enable that, but whether or not that allows us to solve every single problem that we care about is a different question. So I think that one thing that we're looking at is different algorithmic scaffolds to look at. So for example, cutting point algorithms were kind of, I think that if you look at the way that cutting point algorithms are discussed by classical optimization folks, is that they're very nice for their theoretical guarantees, but most commercial solvers don't implement them, right? Because there are other algorithms that are more practical, that have a practical speed up. So one thing that we're looking at and actively working on is extending this framework to include interior point methods, which tend to be used in commercial solvers. So there's definitely work to be done in terms of squishing down this green line even further, or at least flattening the scaling of that.
Okay. All right. That would be the questions from my part, at least. I think at this point, if there is no further question, thanks everyone to join this week's Autonomy Talk, and special thanks to Robin for the great presentation.
Awesome. Thank you, guys.
Thank you. Bye-bye, everyone.